Sorry?
We had a thought for the geometric field edge is halfway through that.
The geometrical field edge is halfway through that, yes.
The penumbra is just the outside of that, so it's part of it.
No, the definition of penumbra is that. Typically, when you ask for quote the penumbra or the beam, you say either 90 to 10 or 80 to 20, which means it's both sides of the 50. Right? So that's what the definition is. Now, clinically speaking, if you want to look at how much larger the field size needs to be than the tumor, then you might want to think about half of that penumbra, but the penumbra is the full size of that. In fact, I mean, if you looked at the drawing, that's what I was asking, regardless. Right?
Yep.
Yes.
Yes.
Okay. Here it becomes the fun side. Anybody? How many people had problems with this? With this question, first question. Okay. Remember, one of the things we talked about is try always to get back to things you know from things you don't know. And in this case, we're trying to actually construct a symmetrical, regular field out of these fields. And the way to do it is to think of the fact that if you put 4 corners in here, what's left over, even though it doesn't look like it, it's another square, but at 45 degrees. Okay, and the size of this square would be, what's Pythagoras theorem? Anybody? AB plus B square, A square plus B square equals C square. You still get taught that at school? Yes, you get. I don't know, maybe they do it all on a calculator now. So, if this is 6 and 6, this diameter is 8. The diagonal is 8.49, therefore you end up with an 8.49 square if all of it was blocked. If none of it is blocked, you go back to a 12 square, and therefore this really is half of each. Therefore the TAR for this combination is the average of the TAR for the two. Which, in fact, if I put the other block there rather than here, would have been exactly the same answer. You see that? Just construct something that you know the answer for, which is this and that, and then if I only put one square, one block instead of 2 blocks, then how would that change? Anybody? If I given this with only one corner blocked, how would this?
3 times the first one and then divide by 4.
Yes, 3 times this one plus this one divided by 4. Yes, it's exactly the same, but not the field size. You need to do that. Is the TAR you need to do that. So you have to take the TAR for this and the TAR for that, and then do the sorry.
Can you say again how you change it?
Well,
if it was just one block.
Well, since it's 2 block, this half looks like this half looks like that. And therefore it's equally weighted. If you only have one block, 3/4 of the field looks like this, and only 1/4 of the field looks like that.
Okay.
So you take 3/4 of that TAR and 1/4 of that TAR. So in other words, don't average or the area or the field or the side of the square. Just look at up the TARs and average those. Now Now this was a little more challenging. How many people had problems with this one? Okay. This one is more challenging because you need to use your imagination a little more to construct something that is symmetrical around the point that you're interested in. And the way to do that is to put another field on the other side. Alright, so this is a 10 by 5 and another 5 centimeters. So 5 centimeters further, you put another one like that. That makes it symmetrical around this point. So what you now have is the 30 by 5 field, of which the middle 10 by 5 field has been subtracted. So you look up what a 30 by 5 field, which is an equivalent square of 8.57, and a 10 by 5 field has an equivalent square of 6.67. Notice how the TAR doesn't change very quickly from 6.67 to 8.457, even though it's such a large, because as further you go from the center, the scatter gets less important, less scatter gets back into the center. And that's why the TAR table sort of curve. So what you have, if you had this field and then block this part, what you will get at that point is only the scatter from these two sides of these two open out of the fields into there, and you get that by taking the difference between the two. Remember, tissue error ratio is primary plus scatter. So this is primary plus scatter. This is primary plus scatter for this field size. This is primary plus scatter for this field size. You subtract the two, you subtract all of the primary, and you're just left with a scatter from those field sizes. But however, my original question only had one of them. So after you take this, after you subtract them, you have to divide by 2, because this one is virtual, it's imaginary, it's not real. Okay. This is just a way of stretching your sort of your thinking faculties. Now, the other thing interesting to see that there is compared the. In other words, this is a correct answer for the TAR of a point outside of the field. So the point outside the field has something more like 1% of the dose at the center of the field. That's a scatter that, for coals especially, there's scatter outside the field. So that's real dose that's coming because it's been scattered in the water phantom outside of the field, and you can actually measure that kind of dose outside. So each of these questions has more than one point. One is to do the math, and also is to teach you something about the physics. There is those outside fields. Sometimes the doctors forget that. You are a physicist, you have to remind them. Typical case, they treat a patient to 50 gray parallel opposing, which include the cord, and then they cut the field to just be in front of the cord and give another 10 gray. You have to remind them that those 10 gray are actually contributing some dose to the cord because of scatter. So they have to stop at 40, not at 50, or 45. That's a kind of practical, clinical consequence of knowing that there is dose outside the field. And you are the physicist, you have to remind the doctors of what the reality of physics is, if they forget. Okay. Switching from megavoltage to kilovoltage. people have problem with this question? That's good.
So in the question sheet, you've got the inner homogeneity factor, and there you've got the homogeneity factor. They're the same thing.
I think they're the same thing, yes. Sorry. Sorry, homogeneity coefficient. Is it?
Yeah.
Okay, yes. Well, first couple of things, going back to here, there was not calculate a half-value layer homogeneity coefficient. Well, the half-value layer is the thickness at which the dose drops to 50% of the original dose, and therefore you need to look somewhere between 50.7 and 47.1, but obviously much closer. You need to do some kind of interpolation. The easiest way to do the interpolation is to plot things. In fact, it's even easier if you plot the log of transmission against depth. It gets more like a straight line, so the interpolation becomes even easier. But you can see the first half-value layer is about 0.41 millimeter of aluminium. The second half-value layer, when it goes from 50 to 25, which is another factor of 2 down. And lo and behold, the second half-value layer is much longer than the first half-value layer. It's about like a 0.611. And therefore the homogeneity coefficient is a ratio of those two. And it's always less than 1. If the homogeneity coefficient is 1, it means that these two numbers are these two thicknesses are the same. And that only happens for monoenergetic X-rays, say cobalt-60 or cesium-137 or whatever. And you remember why the amount of material that it takes to attenuate the beam gets more as the beam is being attenuated, because the low energy part of the spectrum is getting attenuated faster than the high energy part of the spectrum. So what you're left with after this point is a much harder beam, which was the point of the next part of the question. If an additional 0.2 millimeters is added to the filter, what will be the half-value layer of the resulting beam? Anybody have issues with this question, with this part of the question? The point being is that if you put 0.2 millimeters of aluminium in the filter, you're basically taking it away from the measurements and putting them on the machine, but this doesn't change anything. Therefore, if you add an extra 0.2 filter, you now have a different beam, and you can figure out what the beam quality is by saying that this is now 0 aluminium outside of the machine, because the 0.2 is already in the machine, but everything else will look the same. So if you renormalize all your readings to 100 at this point, you can then plot a different half-value layer graph, which will give you, lo and behold, a larger half-value layer, because the beam has been hardened by these 2.2 millimeters which have been put into the machine. All right, that's the first part of the question. And the other part of the question, what will be the dose rate relative to the original beam? Well, you have it here. Before, when you put 2.2 millimeters of aluminium, the dose rate had dropped from 100 to 68.4. So if the current is the same and the voltage is the same, the only thing